guys, Miss Miller here. I am looking at the electromagnetism and Lenz's law guided practice problem. And I'm realizing that Mr. Swenson and I have kind of different perspectives about how we think through Lenz's law. I don't think one perspective is better than the other, but I think that sometimes one perspective clicks with a student more than another perspective. So I wanted to present to you kind of my way of thinking through Lenz's law. And then you can choose which perspective is making the most sense for you and applying that in order to solve Lenz's law problems. So the big idea here with Lenz's law is going to be that negative in Faraday's law. It's the direction of the induced EMF that comes before this Faraday's law over here. This part, the negative, is Lenz's law. And what that negative is meant to tell you is I like to think about it as like nature is always resisting change. Nature has a fear of change. It doesn't like change. And so it's going to do everything in its power to resist that change. Okay? So for this practice problem, I'm actually going to start down here in number 2, and we're going to come back to number 1. Okay? So number 2 kind of tells a story. We have a loop of wire that is entering and then exiting a magnetic field. And you can see it goes in sequence. This is 0 seconds, 0.6 seconds, 1.2. So it's like we have different pictures of it at different moments in time. So let's consider just the first two, when it goes from 0 seconds to 0.6 seconds. That's going to be our focus at first. Okay. So I'm going to become the loop of wire. I'm going to feel what the loop of wire feels. I know, seems silly. Stay with me. So as I, the loop of wire, go from 0 seconds to 0.6 seconds, I am entering a magnetic field. So this change occurs. Suddenly, I am feeling all of these little X's of the magnetic field inside of me. And I do not like this change. I want to resist this change. So I feel a gain in magnetic fields that are going into the page. And so I want to somehow resist that change. I want to compensate for it. And so what I do is I create a current. I have an induced current such that I can balance out that gain in X's by creating a magnetic field that's out of the page. After all, the change was a gain in X's, so to resist that change, to compensate for a gain of into the pageness, I create some out of the pageness. Now, how can I create out of the page magnetic field? Well, I am a loop, and as long as I can induce a current in the loop, that current will create this magnetic field. This should remind you of curl right hand rule. When your thumb, the current, creates a magnetic field around it with your fingers curling. So the question becomes, which direction must this current be in order to get these out of the page red magnetic field? So I'm going to scoop with my hand. I'm scooping into the page on the outside of the loop, coming up and out of the page on the inside of the loop. And I see that my thumb is going to be pointing with a current in this direction. So again, to recap this story, I started here where I didn't feel anything. I was just outside the magnetic field. And I transitioned, my loop transitioned into a magnetic field, which means it felt a gain in downwardsness. And I did not like this change. So I wanted to compensate for it. So I induced a current in the counterclockwise direction, in that direction so that it would create a magnetic field that's upward, to balance out this downwardsness change. Okay, so that's how I got counterclockwise current for that transition. Let's move on to our next transition. I'm going to clear this so we can see what's happening. We're going to go from 0.6 seconds to 1.2 seconds. Now remember, I'm concerned about the change, so let's see what I, the loop, have felt. Up here, I'm in the magnetic field. I have a downwardsness, into the pageness. And the next time, I'm still in the magnetic field, and I still feel the same amount of downward into the pageness. There has been no change. There's no change in the amount of magnetic field that I'm feeling. Because there's no change, I'm nice and happy. I don't need to induce a current in order to create a magnetic field to compensate for anything. There's nothing to compensate for. So this loop would experience no current. It's not clockwise, it's not counterclockwise. There would be no induced current. Okay. Let's take a look at our next transition. We're going to go from 1.2 seconds to 2.1 seconds. So we're kind of looking at this transition here. Okay. I felt some into the pageness to begin with. And then I felt less into the pageness because I'm starting to exit this field. I am losing into the pageness, and I do not like this change. So I'm going to try to compensate for it. I'm going to try to get some more into the pageness. Because I don't like losing into the pageness, I'm going to create some more for myself. The way that I create that magnetic field is by getting a current, inducing a current. So the question becomes, which way must the current be induced in order to create an into the page magnetic field? I'm going to use my curl right hand rule. It tells me that a current carrying wire can induce a magnetic field. My thumb, the current, induces a magnetic field. My fingers. So I'm going to try to make my fingers go into the page on the inside of the circle. And when I look at the direction of my thumb is going clockwise. So this would be a clockwise current. Again, to recap, I lost some into the pageness in this transition as I'm exiting the field. And I didn't like it. So I created, I induced a current in the loop such that it would create a magnetic field that's into the page to compensate. We have one more transition here. From 2.1 seconds to 2.4 seconds. Again, looking at the change, I had a little bit of into the pageness to start, and I had no into the pageness at the end. I again lost into the pageness, and I don't like it. So to compensate, I'm going to create some into the pageness. And I create that into the page magnetic field by inducing a current. Using the curl right hand rule, I can figure out the direction of that current, just like my previous one. This would be clockwise. Whew, okay. So with that in mind, I want to return to question number 1. Now, for question number 1, it's almost like we have to think backwards because we are given the direction of the induced current, and therefore using the curl right hand rule, the direction of the induced magnetic field. And we have to figure out what it was reacting to. We have to figure out the direction of the original magnetic field coming from this magnet that's moving in or out of the coil. So let's try. Part A should be the easiest one because part A doesn't show any velocity, which means that I can assume that this velocity is 0. It's not moving. So if it's not moving, then there's no change. There's nothing for the coil to react to. So I don't really care. This could be a downwards or upwards magnetic field, meaning this could be north or south. There's no way of knowing without more information, but because nothing's changing, I can't know. A weird one. Okay. Let's take a look at part B because that's a little more interesting. Okay. So I, the loop, I have induced a current going around me. And I've induced it such that when you use the curl right-hand rule, you find that inside the loop, there's this magnetic field pointing upwards. I must have been trying to compensate for something. What could I have been compensating for by creating an upwards magnetic field? Well, I must have been compensating for gaining some downwardsness. So the question becomes, what must have happened with this magnet in order to gain downwardsness, causing me to react with an upward magnetic field? Well, because my magnet is moving downwards, that must mean that my magnetic field was downwards. Because as this magnet moves down, it would cause me, the coil, to gain downwardsness, reacting by inducing a current such that its magnetic field is upward to compensate. Now, whenever you see a magnetic field line coming out of a magnet, we know the convention says it comes out of the north. The other side, therefore, must be south. Let's try part C. Okay. I, the coil, have induced a current going this way so as to create a magnetic field, using my curl right-hand rule, a magnetic field that's downwards. I must have been compensating for something. What would make me compensate with a downwards? Well, I must have either been losing a downwards or gaining an upwards, right? I would have to balance it out. But take a look at my magnet in this case. It's going up. We're taking that magnet and pulling it upwards. So if I were to make the magnetic field of the magnet downwards and then remove that magnet, that means I would lose downwardness, which would then make sense that I have compensated with a downward magnetic field and a current that would create that. Looking just at my magnet now, when I have something coming out of a magnet, I know it must be the north end. Okay, I want to leave D and E really just for you. I want you to reason through this. I will tell you the answer here should be south and south, meaning that your magnets are oriented like this. So you can check yourself. But just like I've talked through what must be happening to cause the coil to create a current to compensate with a magnetic field, I want you to talk through that story too. Okay. I hope this was helpful. Again, I know it's a different perspective. I know that there are multiple ways to think about Lenz's law. This is a way that makes sense for me. It might make sense for you too.